Hello, my name is Joshua Chung, and today I'm going to talk about using assemblies in CAD, and especially Fusion 360. And I'm going to start off with a project I did over the summer, and it's a telescope. So the one I was trying to design in Fusion 360 was a bowl telescope, in which it uses a bowl on the bottom as a fulcrum to move your telescope instead of a traditional camera stand, something like this. And just briefly, in CAD, it will look something like this. So you have your telescope here and your little bowl down here, and you have your attachment pieces here. And you get something like this in a 3D space on your computer. And the way you would do this is by using assemblies. So what assembly is it's basically a collection of the parts you designed or the parts you have gathered from somewhere, and you're combining them into a bigger part, such as a telescope in this case. So if you see in this telescope assembly, you can see that it's consisted of different parts, such as telescope is consisted of different thick supports, different sticks, different primary mirror holders, your primary mirror holder, your secondary mirror, and your focuser holder. And the reason why you would be using assembly is basically you don't want to design all your parts in one CAD file. So if I have this, I actually have, where is it? The telescope I made over the summer. And as you can see, it's quite big. And these are the parts that are actually 3D printed and designed. These color prints. They're colored because I used coloring filament. I just wanted to try it out. And as you can see, it's all consisted of different parts. And in most cases, you're not going to use all manufactured parts. Something like a telescope, in this case, I use wooden dowels as the structure. So what you have to do is divide your parts into different categories or different parts you're going to design in. So in this case, I decided to design the parts in, I guess, major structure points, such as the thick supports, the primary mirror base, your primary mirror holder, and different parts that it's actually structurally needed for the telescope. And instead of actually telling you how to design these parts, because it's kind of difficult to understand how you have to design them, I'm going to go over what assembly is in general overall, and then later explain how to design them using those assembly constraints. So I'm going to start off with a simple file. And I already previously designed these telescope parts, so I don't have to redesign them again. But I'm going to start off with the, where is it? The thick support. This is what our whole telescope is based off of. When you insert your new design into your design area, you will get something like this. It will be highlighted in blue, and you will have all your 3 plane movements and your rotation movements. In this case, you can move it around like this, 90 degrees, and dictate it if you wanted to move a certain degrees here, just manually. But in this case, we're just going to leave it as is because it's perfectly fine. And now we're going to insert the sticks like this. And in this case, it happens to be that it got inserted in a vertical orientation. And so if we wanted to, we can just switch this to 90 degrees and go to the right side and try our best to insert it. This. extrude it like this. And if you press OK, it comes out like this. To us, it looks normal, right? It should be there as it should. But what Fusion 360 doesn't do is it doesn't memorize what the locations of these individual parts are at. So when you decide to, I guess, move a part, it's going to only move that part and it's going to misalign everything, as you can see. And if you want to move this again, you have to do something like this and put it back in. And it's quite tedious, right? If you want to move a certain design or this file a little bit to the left, like 3 millimeters, you have to shift everything that's connected to it by 3 millimeters, which is quite annoying. And so Fusion 360 provides a tool for us to do that. And that is called joints. And what joints are basically constraints that you put on a 3D object between two different features. So if you press the joint program, joint method, and we get something like this on the screen, we can choose between position and motion. They're actually the same, I guess, program. They're part of the same idea, but they do two different things. So in motion, you can decide what kind of constraints you want to add on to your parts. So there's rigid, revolute, slider, cylindrical, pin slot, and planar and ball. So what rigid does is it basically glues the two parts together. So if we go here, we're going to, 1 second. If we want, we can stick this plane onto this plane. And to do this, this allows me, there we go, select it. This works. 1 second. 2. It's not working. I guess it's not working as it's intended, but what joints do is basically it constrains two different parts into the right constraint you want to set it to. So let's say you want to put this stick into this coaxial movement, coaxial hole. Coaxial hole, and you can do it using 3 different methods, such as revolute, cylindrical, and pin slot. But we're going to use revolute. And when we choose revolute, we can do 3 different. We can do many things, but we can choose which features we're going to snap to. So Fusion 360 is pretty intuitive on which features you want to select. So if you click snap on the first component, we can click on what axis you want to snap the revolution feature to. So such as, in this case, it's going to be the axis of the stick and the axis of the hole. It allows me. It goes here. And or should allow me to do it right there. If not, I don't know. Okay. There we go. Now it allows us to actually move it to the place we want. It allows us to, I guess, confine the restraint that we want. And in this case, it did revolute. And what this does is it constrained the stick rotation movement to the hole's rotational movement. So if we double click on the feature, we can turn this however we want. However, sometimes you want it to move linearly as well inside the cylindrical movement. And we can edit this by clicking on the joint set. If it lets me. I guess I have to do it manually. If we do joints and do cylindrical, we can do equal axis movement here and your movement on this axis. So here, it's like this, right there. We can do something like this. Now we can adjust the lengths of where it's going to be placed in. So if we press OK, now we can dictate how far we want to move up and down. If this is, if this is actually in place. But as you can see, if we wanted to move back and forth, it's moving both the parts. It doesn't know which position it's going to move relative from. And Fusion 360 does this definition by grounding. So when you click on your main part that you're going to build your product off from, you can right click it and ground it so that it's in place. And now it is cylindrical. There we go. Now we can move this freely like this. And this also means that from now, this the thick support on the telescope is not going to move. It's grounded potentially in a way. And now we can just copy these onto the three different holes and apply the different joints. And I'm going to do it again. But in this case, I'm going to try to do a rigid if it lets me. I'm going to rigid this edge into this edge right here. And now in this case, it kind of stuck to the axial movement. So now what this does is for the cylindrical movement, we can move it side to side. But now rigid basically glues everything. So it's not able to move. I'm trying to click on the stick and trying to move it, but it's not going anywhere. So you would use these joints in many different applications. In some cases, you would use rigid for, I guess, parts in order to stick together, and cylindrical if they're moving parts. But in most cases, you're going to just stick with cylindrical because you want it to be able to move back and forth to adjust it slightly for the visual appealness. And I'm just gonna copy this really quickly. And now in this case, this is the difference between grounded and non-grounded. The stick can move, but this stick cannot. So what grounding additionally does is if it has a feature connected to the other files, such as this stick and this file, this stick will not be able to move because it's grounded technically because of the thick support. So if we do a simple rigid joint again on here and here, it'll stick there, and then one more time, something like this. Joints, motion, select the movement here, and then snap to here. It's okay. And now we get the basics of the telescope. We get the thick support that's grounded, that does not move, and we have the 4 different sticks that are coordinating the structure of the telescope. Now we can copy paste the thick support later on. And when you copy paste it, it actually deletes every single feature that's on the original file, I guess, file you're working on, the original body you're working on. So now this product, this file can move freely. It does not have the rigid constraints that it's holding back the first support. So what we have to do is apply a joint. And in this case, it would be fine to apply a rigid joint because the angles are pretty similar. But if we potentially do it wrong and it's tilted off a slight bit, we get something like this. The final support is tilted a little bit, but now since it's rigid, the constraint, it can't really rotate anymore. All it can do is basically be stuck on this. But since this joint is actually rotatable, we can adjust it a little bit using this guide. But in most cases, you really don't want to do that. You don't want to define your constraints from other constraints that you might change later. So what you would do is you would modify the constraint so that it is a revolute. So you can independently change it. So in this case, now I can independently adjust it so that it's not dependent on anything. And if it's like this, as you can see, it's kind of tilted by a little bit. So if I just find the right angle, I guess it's negative 12-ish, 10, 11. 11 is close enough. We get something like this. And if you notice the little tip that's sticking out, it's because of the cylindrical movement that we initialized up here. We just move it back here and we get something like this. We get the basic frame and that's pretty much it. And I'm also going to ground this so that it doesn't move anywhere. And when we ground it, we get something, we get some warning almost. It says some components have been moved. And then it says capture position or continue from the previous position. In most cases, you want to capture the position. What this means is what is on the screen is going to be captured. So if we capture it, it will be off. Oh God. It will reflect what it was right before the constraint. So if we undo the ground and adjust this again, I don't know why it's so off. Negative 11. Give me 1 second. And now ground this. Capture position. There we go. When we capture position, we get something like this. It captures position it was at. But instead, if we decided to continue it, it will start at the angle it was originally, I guess, constrained at, something like this. If you remember, it was kind of rotated a little bit, and it keeps that in memory, and it will just refer back to that when it's constrained back. So in most cases, you just want to capture position so that it keeps the relative position it's at. And this is basically the basics of assembly. You have joints, which have the majorly 6 different types of joints, right? But there's also something called built as built joints. And what this does is it does it in relative terms, but you kind of want to stay away from this because in your design, you should technically have features that you're going to define where it's rotating from or where it's sticking from or where it's going to glue together. So you normally want to stick with the joints. But I will show you an example if possible later, but we'll see if time allows. But this was a simple approach to what the telescope thing was. But now we're going to go off into a little bit more complicated stuff. And one example is a finger, if I have one. And this was a project I did for actually a writing class last semester for final. And I was making a hand. And because of this, I had to make the individual fingers. And what do fingers do? They rotate at the joints. And this is what rotational could be utilized for. So what this, I guess, part of the design does is if you have a servo that rotates and pushes this arm a little bit forward and backwards, it's going to move the finger forward and backwards. And this is a unparalleled reverse 2-bar, in which it allows the moving bar to rotate 180 degrees without the need of having it parallel. So a normal parallel 2-bar is going to have the 2 bars, the lift bar and the moving bar at the same parallel, I guess, constraint. But in this case, we're able to modify it by using it as a reverse unparalleled 2-bar. And I will bring it real quick. This is what the project I did over, I guess, 3 months ago. It's consisted of those 5 different finger modules, and it moves like this. So when you move the servo arm, it's going to contract the finger and open it again. And this is where you're going to use most of your rotational constraint from, not just some random sticks you're going to put into telescopes. It's where you're going to rotate different objects too. So in this case, we can start off with just hide the necessary stuff. We can start off with the plane, where we're going to have I guess, fingers starting from. And we can have our stand. In this case, the stand was, I guess, plainly designed. I believe so, yes. So it's stuck on there like rigid. But now, if we add the fingers, it's for the finger part. It's constrained rotationally with a rotational joint. So you would do this simply by going to joints again, and then between the 2 different parts, you're going to click on the different axes. So component 1 will be right here, and component 2 will be right here. I already have done it, and you'll get something like this. Initially, it seems pretty simple, right? It's just 1 bar moving from 1 axis. But if we introduced another bar up here, the upper finger, there we go. There we go. We have something like this. It's if we add another connection here up front and back here, it's connected axially again with a rotational constraint. It's just going to simply move it up and down with the lower finger. And it's because currently it doesn't have any rotational constraint. So if I move this down, if it allows me. Delete that. Delete. So now, if I have this, I can move this now freely. But since you don't have any rotational input when you're moving the general finger, it's going to stay stationary in relation to your lower finger. And in most cases, all your joints are going to be relative to each other parts. It's not global. You can't really stick anything. You stick a physical object onto anywhere in the 3D plane, the 3D, I guess, corner plane. You can stick it to a plane, like as if you're sticking on the ground, but in most cases, you're going to be sticking it to other parts. And that's what the joints do. And if I revert back enough, like this, there we go. Plane, stand, this. this. And if we add the final part to our finger, the bent connection, we'll get something like this. These now, the holes on the upper ends of the upper finger and the lower side of the stand, when they're connected, it's going to start contracting and just pulling it back. This is where most of your, I guess, moving parts are going to be jointed. It's all rotational movement, such as like wheels on a car, engines, or anything that moves in a circle. You're going to use circular joints. And one thing from assemblies is that you're not constrained to the parts you made. You can also design it with the assemblies you have made. So if we have it here, give it 1 second. There we go. You can build it with the assemblies you have made. So in this case, this is a different finger file. I kind of redesigned it during the process, but these individual compile3 files are actually assemblies that are consisting these different finger designs. So you can have assemblies after assemblies after assemblies in your assemblies. And it's quite useful if you're designing small intricate parts, such as a hand in this case. And you can also design from your assemblies as well. But it's going to be kind of constrained to not having, I guess, the snaps. So if you remember in normal design, right, you're going to have these snap points where you're going to snap, where you're able to snap. So your line can snap to the 4 quadrants of your circle like this. But in a 3D design, it's kind of difficult in order for the computer to actually determine where those snap points are for all the parts. So Fusion 360 kind of denies all of those snap points, and all you have is basically a 3D corner plane, and you design your part as closely as possible. So in this case, for the bodies, I had to design it so that I was basically just looking over 5 sketches. There are many sketches that I had to go off of, so enable everything and disable everything. This. 1 second. There we go. Bodies, go away, go away. Show the sketches. As you can see, I had to go off of just looking at where those individual fingers were and roughly design and roughly just draw a line of where they were. And this is kind of bad designing. You really don't want to do this. You want to design it so that it's well planned out. You want to bring this as a separate model into your design file. But I really didn't have the constraints that I needed to actually design it, like just from a separate file. That's why I had to combine everything into this one file for the fingers and then design from there. And I believe this is the first design, so it doesn't line up correctly, but this is roughly what I did for the hand. So yeah, you can have multiple assemblies in your assemblies. And building on from the complex rotational movement in a finger, I guess I'm going to go a little deeper into a more complicated rotational movement project that I did, and that is the mechanical tulip. So if you weren't here last week, I'll just give you a short introduction of what this project I was working on last week is. It's basically a flower, a 3D printed flower that moves by a stem in the middle. So if I move the stem up and down, it will open up the flower petals and close it respectively. And it does this by having, I guess, 3 different joints similar to the finger on one axis. What I mean by that is if I hide everything, second, only highlight the ones I need, like this. Fusion 360 is really happy with multiple constraints working with one another. It just has to match perfectly, else it's going to error out. I'll show you a quick example later, if possible, but what this project basically entails is when you have a minor stem just going up, there's a push bar that's pushing the, I guess, your pedal, and it opens it up by having it push using this little piece. And with this torque that you apply right here, it's going to just open up your flower petal, close and open it. And in this case, you saw that it kind of moved all the way over here. And that is because I have I believe, yes, a cylindrical joint instead of a revolution joint. So what this basically does is, if it's not constrained properly, it's just going to move all the way over here because it doesn't know it has to stay between these 2 lines, between these 2 parts. There is a function that Fusion allows us to detect 3D physical touches, and that is in assemble, and that is in enable contact sets and enable on contact. But I kind of stay away from these because it's really intensive on your I guess CPU, and you probably need a stronger machine than a MacBook to actually analyze and detect all the individual points in order to simulate that 3D interaction. So what I mean by that is, if you have 2 gears in assemblies that you designed, and you want to actually mesh it together with physical interactions, it is possible to do it with these enable contact sets and enable all contacts. But it's probably going to take at least 6 hours to calculate all that movement, and that is only for a fraction of a degree. So it's basically impossible to use unless you have a powerful computer. And because of that, there is a tool that Fusion implemented, and that is motion link. Capture position. Just going to enable everything. And what motion link does is, slide 1. There, it allows me. It takes a while. I'll make sure to come back on it, but it makes it so that it's able to move the joints. Oh, that's slowing down my computer now. It makes sure it slows down the. Give it 1 second. Now, buttons again. It basically simulates that motion without having to do those physical interactions. So it's something like this. You can't really see it, but it's just doing it on its own. And how you do this joint-wise is pretty easy, actually. I had to go through several prototypes of getting the right lever length and the right lever, I guess, size. I can show you guys a quick show. So I had to basically design a quick part of what the right lengths are going to be. So in your, I guess, 3D designing career, if you want to quickly determine how long it should be without having to design all individual parts, you can do something like this. You can have multiple parts with just holes extending forward. And this way, you can just switch out the different joints and just experiment it as you go. So let's say I want to, instead of having it at the 5th hole, I want to move it. I want to change it so that it is delete. It's moving, I guess, at this 7th hole, 8th hole, not sure. But let's say we want to do that. Then we can just quickly change it here and just do quick movement. Not sure where it's selected. There we go. Select this and then select this one again. Now we can just switch. It enables us to quickly change which feature we want to see. So now it's a little, I guess it opens a little too quickly in this case. And the bars kind of hit one another. So it's kind of impractical. So if we just quickly go back, change it, we can just go change it. And this is what it looked like before. And it works out okay. And this is kind of gets in check in most cases. You don't know what it's going to like. You don't know if you don't have a design you're basing off your assembly from. You don't know how far you should push your push rods to, how long the minor stem should be, how long the leaf should be. So it's a quick way to test how you should do this, how you can design it later on. At least for this project, I was able to do this quick joint assembly and determine the right lengths between the holes and the angles it should be at. And that's why I was able to guess the correct let's show you the correct lengths between the two. So if you see here, it's basically impossible to design it so that it's perfect on the first try. I had to iterate it through at least 3 different times to get around the animation that I wanted. But that is it for rotational movement. And now, if you were here last week, we designed something called a chair. And it was a very interesting chair. If I can remember. It may not be in my mechanical tool. And we made this chair. It's quite interesting. I'll show you the quick design progress using Fusion's tool of allowing us to do that. I think this tool is pretty cool. It's pretty easy to use. It does it automatically, not doing anything special. But basically animates the whole progress just by going through what the process was. However, if you think about it from a manufacturing perspective, it's quite impossible to just 3D print this just as is. We saw that it's possible with the support and through just a lot of rotational adjustments, but there are better ways to manufacture this, such as manufacturing just the top part, the 6 different individual legs individually, and then eventually going to the center and design that area, this part. This, I guess, chair-looking part. The way you would go around this is basically there are two different ways. First, you can cut apart your design from your original file, or you can just create it from scratch using different models. But the first way is if we create a sketch and just cut off where it's going to be at, such as this, and draw a rectangle of where it should be. And sketch. And just, if you cut the top part out and do a two-side extrusion, you can cut this and do the same thing for the chair legs, and just 3D print this chair part. And then later on, add this back, then extrude this. Do symmetric now. Do intersection and 3D print this part. So this is probably the most common way you're going to divide multiple your large pieces into different sizes, so you can actually print them. Or, as I said before, you could just think about how you're going to manufacture this part. Like I said, like we saw last week, it's impossible to 3D print this pretty well. It requires a lot of support down here, which basically takes all the material on, like, between the surface, between the wall and the support. Very rough. It leaves the surface really rough, and there's going to be a lot of post-processing. And it's basically making your product from scratch in a way. And what I mean by that is, if one of your part breaks, you're going to have to reprint the whole thing again. And it's quite inefficient overall. It's wasteful and it's poor designing. So you will normally go off of your second, the second method, designing it so that you already know how you're going to manufacture it and designing off of that. So if we look at this chair, for example, we can see that these legs could be made of something else, such as metal PVC pipes, wooden dowels, or just steel rebars, if possible. So what you would do then is, I'm going to delete these if possible. It's loading. Oh. You can actually introduce divots in your file right here. So if it's possible, circle, sketch, do an offset plane here. A circle. So you would create a design in a way that it's something close to this. I will cut this off as closely as possible and extrude these so that it creates divots into the main chair part. If it's possible. Never mind, it is not letting me do that. But you would create your parts so that you have your divots in here. And actually, I'll try to see if I can do it right now. Create a line, this plane, right here. It's not letting me do that, but the whole general idea is you would put divots in here and make sure you can put those sticks inside and, I guess, design off of that. And you slowly start learning these, I guess, design steps when you're slowly designing them and just overall producing your parts. And you really don't know until you start designing them. And as for the top piece, I mean, this overall chair is kind of awkward to manufacture anyway. So I don't know why you would create it, but if you had to, you would first print this upside down, create screw holes right here, and then put the seat, print the seat up here, this part, and then screw it in down here again. And then similarly to the legs, you would screw it in and then go on from there. And before I finish roughly, it's not scary to actually divide your parts together as it seems. If I go to my first project, this is one of the projects I did over the winter break. There is one, find it. This is actually a resolution calendar that I made. Sure. So it's something like this, right? You would click on you have two buttons to operate, to engage, you did your resolutions, or to go back, and to incomplete your resolutions, you can do something like this. But this is kind of hard to print. It's 40 millimeters in length, and it's basically impossible to print on your normal 3D printer. So you would normally just divide these into divide your file into two different products with two different files and glue them together. And it seems kind of bad in a way, but it comes out pretty good. It comes out pretty well. So this is kind of the glue you get. It's kind of, I use super glue in this case. But if you manage to sand it down, primer it, and then just spray paint it nicely, you get something that's actually kind of good looking in a way. So if you have to create your part in one file and cut it down, you can. You shouldn't be scared of having to know all the constraints beforehand and designing it off of like that. So in this case, after designing your whole product, similarly to the chair, well, officially actually doing it, you would cut off your piece around the middle area, cut this off, and then you would export this as an STL. For sure. And then go back. Instead of cutting it, you would do a intersection, and then now save this as an STL. And when you save these as STLs, if you go on desktop, you get two different files which you can print pretty easily. I tried to design it so that it prints nicely in a way, but in all, it's definitely possible to cut your parts and eventually glue them back together. So you shouldn't be scared to do that. But yeah. One other example of assemblies that you might use is using outside products, outside designs that you basically did not create. And it's definitely possible if you're working on a big project group such as Vex. So for last year, I was able to design my product, design our robot. Using the files that Vex provided us. So in this case, let's see. Give it 1 second. It's quite the file. It's pretty big. We'll see if it opens today. Yeah, you can basically bring in outside files. An example might be I guess, servos for my, I guess, fingers. You don't have to design your servos by hand. You can get files from, in this case, GrabCAD, which is free in most cases. You can just get the file you want and download it as a appropriate file that Fusion 360 understands, and then go from there. So there's no need to, I guess, reinvent the wheel in most cases. There is a product, if there is something that people commonly use, it's going to be there. And this is the robot that I was able to CAD. It uses Vex provided CAD files. And it's pretty nice if the files that they have CADed is good looking. And in some cases, your colors do not transfer over. So what I mean by that is these rubber bands, in most cases, they may not transfer over, but in most cases they do. So what I had to do for this project was that first I started with a drivetrain. Just close these off. 1 second. Quite a lot. Start off with a simple drivetrain, and then build off slowly. Actually, I can just show you this. Start off with a simple drivetrain, and then from there add your structural supports, and then go from there. And the reason why it was kind of easy for us to design the CAD parts was because it was already CADed. Like, so no, it was already built. I just designed my parts and I just designed the robot as it looked. So I guess I'll show everything again and then show the. So it will look something like this, where it did, yeah. And in projects like this, small projects, you really don't have to worry about constraints as much as you had to, such as like the telescope project. So you didn't have to ground everything. It could be all relative. You could just eye it in most cases. And I'll show you a quick, I guess, feature of this is that these parts are normally not connected. It's just visually, it seems visually connected because I tried to put it there, but there is the additional cost of if you want to implement every single joint there is on your robot, it's kind of difficult to, I guess, join like 600 different joints in this case. So I just decided to just put it there because that was the best case scenario for us. It wasn't really a model that we designed off of. It was a simple design that we could just backtrack if we needed to. And yeah. And I think that is it for assemblies using CAD.
Thanks, Josh. So I guess at this point, are there any questions from anyone? If not, I'm going to plug our survey again. You guys should go take it. I put the link in the chat. The grant that this club is a part of wants feedback from you guys. Also, I want feedback from you guys, so we can figure out like what kind of modules you guys want to see next semester.